Hi everyone, thank you so much for joining us today. We have with us Dr. Lehnert. He is a postdoctoral researcher as part of FAIR team at Meta AI. His research focuses on underlying computational principles of intelligent decision making and how intelligent agents can generalize. In this session, he will be talking about the latest paper, which got quite famous and is a very important paper on planning with the help of transformers. So thank you so much for joining us today, and I will pass it over to you.
Okay, well, first of all, thank you for the invitation. I'm really excited to present our project here that we've been working at FAIR at Meta together with my colleagues Zaina, Andy Odigia, Qingqing, Paul, Michael, and Yondong. So, as you probably all know or are familiar with, large language models and transformers have enabled tremendous progress in various application settings. But while these methods or these models have shown impressive capabilities, they still seem to struggle when it comes to sequential decision making and planning and reasoning. How to endow language models with the ability to plan is still not very well understood. So, and in that context, what the question we wanted to look at, or the first question we wanted to look at in this project is, how can transformers be trained to robustly solve complex planning tasks? So in other words, how can we instill this ability, at least to some extent, into a language model or a transformer? But moving past just learning how to plan or training them how to solve planning tasks, we also look at the question of how can transformers be used to discover new search methods. For example, algorithms like A*, which is what we're going to focus on in this project, compute heuristics in order to guide further, to make predictions about future outcomes and guide the search in order to improve their search efficiency. And what we were looking at is something like improving or discovering new heuristics or new search methods is actually possible in that context with using transformers or language models. So in contrast to existing work, the way we approach this is by not looking at large language models and not actually fine-tuning or prompt engineering. We're using synthetic data sets that we construct ourselves to train a language model or an encoder-decoder transformer from scratch to imitate A* search. So we're not at this point really aiming to replace A* search as a planning algorithm. We're really looking for, can we instill or can we implement this type of search and this planning process in a transformer or in a language model itself? And more importantly, what this project is really geared towards is to better understand what influences the performance of language models when you actually start exposing them towards planning and sequential decision-making tasks in a controlled experimental setup. And the controlled aspect is very important here because, again, we're looking at synthetic data sets and run relatively well-defined experiments here. Okay. But the methodology of how we approach this is very much along natural language processing and the usual pipeline of how you train a language model itself. So what does that exactly mean? So let's look at an example first, just as a toy example here. So imagine you have a 3x3 grid and you want to go from this green start cell towards this goal cell, and you cannot cross into a wall. So the optimal way of solving this, the optimal plan, is to go down, down, and then right. And that is a 4-step plan. It's feasible because you're not entering a wall, you're not starting to teleport across that grid, you're really just making 1-step moves. And it's also optimal because it's actually the shortest way to reach the goal condition from the start condition. So what we're doing in this project is showing how you can express the task, the planning operation, and the solution in a synthetic language, or in a synthetic machine language. And here's one example of how to do this. So imagine we basically cast this task as a prompt where we say, okay, you start at 0, 2, you go to goal 1, 0, and we have 2 obstacles at these 2 XY coordinates. That is the prompt that we would prompt the system with and say, here's a planning task. This is the information that you need to know in order to solve this task. And then on the right here, we basically just write out what the optimal plan would be. So in other words, the plan is just a machine token here. And you say, okay, you start at 0, 2, then you go to 0, 1, 0, 0, and then 1, 0. So the ordering here is important, but also the formatting of that sequence, because you're really outlining the X and Y coordinates of how you reach that goal condition. So you can call that a synthetic data set constructed to express planning, because we put in as a prompt information about the task and then receive a plan as a response in order to solve the task itself. But planning in itself does not just involve this prompt and response pair of saying, okay, here is a task and this is the solution. It also involves sort of the activity or the computation that you need to do in order to find an optimal solution plan, in order how to get from the starting condition here, the prompt, towards a plan. And of course, depending on how big you make the task, like say how big that grid is, the amount of computation that you have to do varies, and it can actually become quite expensive to find an optimal solution for sequential decision-making task. If you have any questions regarding understanding, feel free to interject, and I'm happy to take them during the talk. So that's sort of the starting point for just expressing, here's a planning task, and this is how you would express a solution in this synthetic language itself.
We have a question in chat box. The question is, can you tell a bit more about synthetic language? What do you mean by it?
Synthetic language. Oh, yeah. Okay. So synthetic language means the following. It's not natural language like English. Synthetic language really means we have a string here that starts out with the synthetic word of BOS. That's one word, one token. Start 02, goal 10, and so on and so forth. You can almost think of it as like a machine language. It's not quite a programming language because we're just listing out these tokens here, but it is a synthetic language in the sense that it's not a natural language as in English, where you say you're in a grid world, it is 3 by 3 of size, you start out at 02 and you want to go to goal 10 or something like that. So it's really just that token sequence here that I make, that we're showing here in a monoscript font or monospace font. Okay.
And a follow-up question: how does it differ from PDDL?
It's a bit simpler. PDDL is actually more elaborate because you define objects and their interactions beforehand. And what we're doing is something simpler because we're basically designing the experiments to say, okay, we built a model that knows how to solve different navigation tasks or so on. I can also comment on that at the end of the talk. But basically, the idea is that when you look at the prompt itself, the prompt have that for let's say these mazes, the simple structure of you start here, your goal location is here, and you have these wall positions. It's not quite as rich as PDDL. Okay. So how do we actually express this entire process of doing computation, that is the planning computation of arriving at an optimal plan? So when we picked A star, mostly because it's a simple algorithm that we could just study, A star has a frontier set and a closed set of nodes, and it computes basically an optimal plan by doing tree search on this frontier set and closed set, and manipulates these two sets. So just to illustrate how this is done, you start out by inserting the start location into the frontier, and the way we record that in a trace is by saying, okay, or we just write it out here on the slide on the right, by saying, okay, we create something into the frontier with location 02 with a cost since start of 0 and a heuristic value of 3. So we tokenize these as C0 and C3 because those are costs to distinguish them from XY coordinates. And then what A star does, it closes this node from the frontier because it has just one node in the frontier at this point, expands into the next child node, here highlighted in blue, that has now a different XY coordinate and different cost values associated with it. Again, because that's the only one in the frontier, it closes this node. Then it expands into 2 different child nodes and then keeps searching, closing that node, and so on and so forth until it has reached the goal condition itself. Meaning the moment a goal state is closed, the system has, or the algorithm has found a plan and can then just output, given the computation that has been done, the optimal planning sequence here on the right. So what this does is it really outlines how A star would sort of compute or think about a particular planning task and then arrive at a plan at the end of the whole computation. And this is how we basically capture planning as, like, let's say, the computation in a synthetic language. Again, synthetic language means literally the words that I'm showing here on the slide, where the prompt starts out with the beginning of sequence token, start 02, and so on. But now the system, if it wants to predict the computation and not just the plan itself, predicts a lot more tokens of a different kind. It predicts, let's say, a create token here for every insertion into the frontier set, every time a node gets created by a star, and then predicts the XY coordinates along with the cost values and so on and so forth. So this actually gets, when we train the model, this whole trace gets truncated or gets collapsed into one very long sequence of tokens. Now, one thing that I think is noteworthy about how we constructed this, because it might seem a bit arbitrary, but it's actually not. So if you were to take the prompt and any prefix here, let's say you take the first 5 lines here that are not grayed out, and given that prompt and given that prefix of the execution trace, you could take that information, parse all that, and then reconstruct A star's intermediate execution trace as it is planning at some intermediate time step. Basically, so basically what this is highlighting is a snapshot of the computation itself that has been done so far. And you could reconstruct A star search and then basically say resume, like as if you're doing this in the debugger, and then just say resume, and it would execute as before and find an optimal plan. So in other words, what we've done in terms of constructing these traces is we capture enough information such that you could always reconstruct A star's execution trace and then just hit resume or basically continue the computation itself. That's why we're saying it is not just encompassing the information of what an optimal plan is, but it also contains information about what computation has been done by A star search in and of itself. And then we basically train 2 different variants. So the data set is, again, pretty simple. We have a bunch of prompts, we have a bunch of execution traces and plans. Those are pairs, and we just randomly create a data set from that. And we train an encoder-decoder architecture on this language model that we call the search augmented model, because the data set is augmented with the search process that leads towards computing an optimal plan. So we refer to those as search augmented. The other ablation is pretty simple. We just take the prompt and the actual solution plan, just the plan portion, no trace in here, and make that a separate data set. And we call these models solution-only models because these models are only predicting the optimal plan. They only predict the solution for a particular task. And then the training pipeline is standard encoder-decoder, basically a T5 architecture with a few modifications in there, where the solution-only model receives the prompt into its encoder, and that encoder provides a feature representation or parameterization for the decoder, and the decoder then autoregressively predicts the plan token string. And for the search augmented model, we do exactly the same thing, except that we actually feed in this trace portion here as well into the decoder that has to get generated by the decoder at inference time later on as well. So that means that the solution-only model only predicts a few hundred tokens, because you really just predict the actual, okay, you go from here to here to here to there. Whereas in the search augmented case, the decoder predicts a few thousand tokens because it also predicts how to search and how to reason or how to plan in a particular task. So that means that when we construct the data set for different maze sizes, we didn't do this for 3x3 mazes, but for, let's say, 10x10 mazes, 20x20 mazes, all the way up to 30x30 mazes, the sequence lengths, of course, become longer because the optimal plans become longer, just sort of in terms of the tokens that you need to encode an optimal solution. But when you encode include the entire execution trace, you're shifting the length of the sequences at least, or increasing the length of the sequences by at least an order of magnitude, up to 6,500 tokens for the 30x30 mazes itself. And of course, the first question that we looked at is, can a transformer actually learn to generate these very long execution traces? And for that, we constructed something that we call the deterministic A star data set, where basically we look at A star as it does tree search, and the moment it has 2 different child nodes that have equal costs as it searches through this tree of where you could be going, we deterministically break the tie. In other words, we always go, let's say, down the left route because we always want to expand the leftmost nodes, for example, in a maze. And when you construct a data set like this, you're not really changing mathematically a star search, you're just making it so that when you generate an execution trace given a particular prompt, the trace is uniquely determined. Like it constructs the data set such that there's a one-to-one relationship between every prompt and every response the system has to generate. In other words, there's only one correct way to answer that. And we do that by creating a training data set and then a test data set that is different, meaning different mazes, different start and go locations, and then test the system if the system outputs the exact correct trace for each of the test tasks. And this is what we're plotting here, or we want to plot here on the y-axis in percent numbers. In other words, for how many test tasks, or for each test task, does the model generate the exact correct response sequence? And then we plot on the x-axis here how many training instances are actually contained in the training data set, and then look at a progression. And of course, you can ask this question of, does it actually predict the exact correct sequence? Because again, we have a one-to-one relationship between prompts and responses. So there is a unique correct response the system should be generating. And we found out that if you give it enough training data, all of the models or variants that we tested reach relatively high performance values. Like we could drive this curve even further by putting more training instances into the training data set, keep training for longer, and eventually it will be near perfect, let's say, or at least above 95 or 90% here accuracy. But what we also found is quite noteworthy is that the solution-only model, which only generates a few hundred tokens, is the worst performing model, despite having a very large parameterization of, or comparably large parameterization of 75 million parameters. The search augmented model, and again, that's the model that has to predict up to 6,500 tokens, is one of the best performers, especially if you increase the parameterization to some extent. And they always outperform the solution-only model that only has to predict a few hundred tokens. So that's kind of an interesting result, because despite having much fewer parameters, these models, because they're predicting the entire search process, actually are outperforming the other baselines that we have in our experiments. And even using a relatively large parameterization to just predict the plans themselves, like performance collapses, especially if you start looking at fewer training instances in the training data set. So in other words, the search augmented models generate the correct responses for up to 6,500 tokens for more than 90% of all the test tasks. What I should also mention here is that the scale at which for which we're looking at token prediction here with 6,500 tokens is a lot bigger than what you would do for even the largest llama models to train them. And this shows that predicting very long execution traces that encode how to reason and how to plan in a planning task is actually possible. And it's possible with something like an encoder-decoder architecture or a language model. But then the next question is, of course, can we actually also model non-determinism in the algorithm execution? And how can this non-determinism later on be leveraged to actually discover something new, a new way of how to compute search or how to search a particular task? And here, in that scenario, we basically made a small change to the deterministic A-star dataset and made that non-deterministic. Non-deterministic really means that when we break equal cost ties in the child node expansion, we make that actually random by shuffling the order. And what this now means is that the dataset is constructed a little bit differently, namely, given any prompt, you can have multiple correct responses in terms of the execution trace and the plan. Specifically, any plan that is optimal and feasible would be a correct response. In the previous scenario, we were looking to make the model really just output one particular plan, let's say this L-shaped navigation. But in this case, for this grid world, you could go in this L-shaped pattern, but you could also do a zigzag. But you could not go, let's say, up into the top right corner. That would not be anymore an optimal plan. So this data set is constructed so that you can have multiple different correct responses given a single prompt. And the data set would then encourage the model to actually model this distribution of generating different types of responses and generating this or imitating this non-determinism that is implicitly encoded into the training data itself. The evaluation scheme here for something like that is a bit different, because now we don't know exactly what kind of response we will be getting, because the system could answer any of the correct optimal plans. So what we do is we just prompt the system multiple times and then just evaluate if the plan that is being returned is feasible and optimal. And everything else, the system could theoretically predict something completely different, but so long as the plan is correct and optimal, then we count this as a correctly responded or correctly solved test tasks. And this is what we're plotting here on the y-axis, where we basically go through our test task set and say, does the model generate an optimal and feasible plan string in 1 out of 64 attempts? So we're being actually a bit more lenient than in the previous evaluation, because we're prompting the system 64 times, and the system has to only return in one of those 64 attempts an optimal plan. So when you make the same comparison as before, all of the numbers will, because we're using 64 attempts, shift a little bit up because we're being more lenient. And this is also what we're seeing here, where we're reaching near perfect performance according to this evaluation scheme for the largest data set size that we tested. But the same progression that we had before still is still present. In other words, the solution-only model that only predicts a relatively short token sequence, only the optimal plan, is the worst performing model at 175 million parameters. And it also collapses in performance much faster than any of the search-augmented models as you keep reducing the number of training instances or the number of training sequences that is fed into or included in the training data. In other words, the search-augmented models, even the 15 million parameter one, is actually one of the best performing models with a small parameterization of 15 million parameters, despite the fact that it has to predict thousands of tokens more and effectively predict a much more complex string. And yeah, in other words, in the low data regime, the search-augmented models that predict execution are always outperforming the solution-only models in our results. So despite having, like I said, despite having to predict longer sequences, we can use a 5 to 10 times smaller parameterization and use about 10 times smaller training data sets and get the same performance level out that we would have gotten if we only would have used a solution-only model that sort of brute force is trained to just output an optimal plan. So one other ablation study that we did in this context is to ask, what if we now, so we kind of have an understanding now how to say, okay, if we include more and more training instances and more different mazes into our training data, we can push for any of the models that we've studied performance towards being almost near optimal. We didn't really find a limitation in our data set there. But what happens if you actually look at different types of task difficulty? Which approach is more robust, and how does performance actually degrade or change in this case? So here I've shown you before the 30 by 30 maze data sets, but we also did basically a comparison towards smaller mazes in this case, to computational requirements, where we plot here again the same performance benchmark that evaluates or prompts a model 64 times on the y-axis. Tests is one of the prompts ending in an optimal, is one of the 64 responses ending in an optimal plan. And if that's the case, then it's counted as a correct task. And then we've just plot on the y-axis in percent for how many test tasks were actually solved correctly. On the x-axis, we then compare what happens if you do this on a 10 by 10 data set, like train on a 10 by 10 maze data set and evaluate on a 10 by 10 maze data set, train on a 20 by 20 data set, and evaluate on 20 by 20 mazes, and the same thing for 30 by 30 mazes. And as you can see, for, I think this is for 100,000 training tasks, the solution-only model degrades in performance much faster than the search-augmented models. That corresponds to the robustness results that we've seen before. But again, if we have a fixed level, a fixed training data set size, and you keep increasing the task complexity, which is you move towards the right in this figure, of course, performance is going to degrade. In other words, if you're fixing the training data set size at a certain level and you make the task simpler and simpler, at some point, every model can actually solve this task. So there's an interdependency between having a complex planning task and also requiring lots of different examples for the model in the training data for the model to robustly solve this much more complex training tasks. So this is what the takeaway is from on this figure here. So in other words, the search augmented models, to summarize, are much more robust to an increase in task complexity than the solution-only models. But again, increasing the number of training tasks seems to be sufficient to reach near perfect performance level on a completely different held out test data set, at least for the search augmented models. And you could probably still achieve that even for the solution only models, assuming you make the parameterizations big enough. Okay, so the last question that we looked at, and that sort of puts the different pieces together that we've looked at and how to make transformers imitate planning, is how we can use them also to discover new search heuristics or new search methods. So in this case, we looked at a more complex task setting than just mazes. We used something that's called the Sokoban puzzle. The Sokoban puzzle is a bit like a grid world in the sense that you have walls and obstacles in there, but the dynamics are actually very different because you have a worker that you can move around, and that worker needs to push boxes towards the different dock locations. And because it's a very combinatorial task where you have to be very strategic about it, the search tree is actually really large. The number of states is the number of different worker positions, box positions, and combinations of different box positions. And even for something like this task, you very quickly go into the thousands or maybe even or hundreds of thousands of different states. So it's a significantly larger task. And it also has a very different transition structure than, let's say, a maze, because you might very easily move a box into one of these corners here, and then you get completely stuck and you can't solve the task anymore. You cannot even reach a solution at that point. So what this means that when you look at a bigger and more complex task is that more computation would have to be done by A star to solve it. It has to go through a much bigger and deeper search tree. And that is reflected by having much longer token sequences that need to be predicted by the search augmented model. So in this case, we scaled this all the way up to 10,000 tokens in the response sequences themselves. And 30 by 30 is actually it's a comparably small data set or task size in this case. But of course, with this longer execution trace, if a model can predict that, it also can be trained to capture much more complex search procedures that in much more larger state spaces and much more complex tasks. The thing with Sokoban is that it's actually difficult to find a good heuristic because it's not just a navigation task where you can, let's say, you look at Manhattan distances towards the goal condition, because you have to combinatorially sort of or be very strategic about where you're going to push which box in order to still be able to solve the task and not accidentally run into a dead end from which the puzzle is basically reaching, well, a dead end state and you cannot recover from that state anymore. So it's actually very difficult to come up with a good A-star heuristic. We just looked at the pairwise distances between box locations and docks, which is not a particularly sensitive heuristic. And as a result, we also have a lot of variance here in this box plot for Sokoban, because A-star search might start exploring and expanding a portion of the search tree that is obviously not going to lead to an optimal solution. So in other words, it's very difficult for Sokoban to actually find or hard code an A-star or implement an A-star implementation that efficiently searches and solves Sokoban. So and in this case, what we looked at is how can we use the language model to actually discover more efficient search procedures more in general. And the way we've done that is as follows. And the way this whole bootstrapping procedure, or we call it search dynamics bootstrapping, works is that it first trains a search augmented model that has learned to mimic this randomness and non-determinism in whatever implementation we use initially to create that token data set with 10,000 tokens in it. Because the search augmented models are mimicking or modeling that non-determinism and that distribution of how you could search a task in different ways, what we want to do is leverage this property to generate completely new search traces, and then start doing a filtering procedure on top of that to filter out what is perhaps a more efficient way to search through a task that is moving beyond the initial implementation of A-star search that we use to generate the training data. And by that, we can move sort of beyond the implementation, the A-star implementation we initially constructed the data set with. And this works in the following way. Yeah. So we first pick we train a 45 million search augmented model on Sokoban. We use the bigger parameterization here because the task is bigger and it's more complex. So it works better to use a bit 45 million parameterization than the smallest 15 million search augmented model. Then, once the training is done on that first data set, we have a search augmented model that imitates A-star search for Sokoban. Then we use that model to construct a new training data set. In other words, we run inference using the training prompts. And for each training task, we generate 32 different response strings. That means the trace and the plan itself. Out of those 32, we filter out the ones that end in an optimal and feasible plan, and then we pick the one that is actually the shortest. And because we have non-determinism in the model, we can actually get an entire distribution of different search string lengths in that data set itself. And if no optimal plan is found, then we just keep the original training sequence in the data set. In that way, we construct a new shorter sequence training data set, which is then used to fine-tune the original search augmented model to basically predict execution traces that are a little bit shorter than before. And then that procedure, that loop, can be incrementally repeated in order to fine-tune the model to provide shorter and shorter response sequences that still end in an optimal plan. This is what the results I want to show in the following slides. And then, of course, as we do that, we evaluate the resulting Searchformer models that come from this repeated procedure on an independently sampled test set. So let's look first at a few histograms. So in this histogram, in this plot here, we have on the x-axis the length of a particular execution trace. Yeah, of a particular execution trace on an independently held out test set of Sokoban test tasks. This is what's plotted on the x-axis for them. And what the plot will show is a histogram that shows how often there is a string or a response sequence encoded in there of, let's say, length 2000, 4000, 6000, and so on, in percent numbers. And if we compare our A-star implementation, we get this black histogram here that shows some type of distribution that reaches actually a few tokens above 10,000 tokens, tokens, because the plan is actually also included in the response string itself. And this is some distribution. That's just the distribution of our data generation process. It's just an artifact that comes out of that process. Now, the search augmented model is trained to imitate this distribution, and you can see that that actually is happening because the search augmented model somewhat closely matches this histogram. It's not exactly perfect because there's still some approximation errors and some noise, but it gets it relatively closely, and it has also these two bumps in here correctly captured. And as we keep on improving the model through the search procedure, what we're hoping to do is basically shift this histogram towards the left without sacrificing performance on the test task set. As we do this for, let's say, three improvement time steps or 3 improvement rounds, we can see that the histogram is pushed towards the left to some extent. So we have a much higher portion of the response sequences on the same that are generated on the same test task for shorter sequences here, and then the histogram flattens out much quicker for the longer token sequences themselves. And just to capture this same result in a slightly different way here, as we keep on iterating for 3 repeats, we can plot here the relative token sequence improvement over A-star, again in percent, and record again for the same test task set. And what we can see is that the search augmented model at the start of the refinement procedure, meaning iteration 0, relatively closely matches that of A-star. As we've seen in the histogram before, it's not exact, and actually the search augmented models tend to generate slightly shorter sequences already, but only by a few percent points, or maybe 1% point in this case. And as we keep on iterating for, let's say, 3 iterations, the sequence length keeps getting shortened and shortened over and so on and so forth until we reach about a 75% length, or slightly less than 75% length in comparison to our original A* implementation. So this shows that this exploration process, where we prompt repeatedly a search or Searchformer model to generate different types of execution traces, actually works, and you can generate different traces that still result in an optimal plan, and therefore sort of optimize the efficiency of the encoder and decoder model in itself. Yeah, and with every step, the Searchformer model outputs, yeah, like I said, a shorter and shorter search trace on this test set. Just to compare, before I said that we're not sacrificing performance, these are the numbers that support that claim. First of all, the first thing you notice is that most on Sokoban, even if you include a 175 million parameter model, search augmented and solution only model, or even a 757 million solution only model, we get relatively good performance numbers in solving most of the test tasks accurately. Of course, the more parameters you put in, the better the performance is. We actually found out that there is a small fraction of the test tasks that are solved with a feasible but suboptimal plan. In other words, the column here in the middle has a few percent points, which captures how many tasks are feasible but suboptimal, or are feasible but not necessarily optimal, are a few percent points higher than all of the tasks that were solved with a feasible and optimal plan. In other words, the lowest or shortest distance. And what we also found is that fine-tuning this model with that bootstrapping procedure initially gives us a performance bump after we do the first fine-tuning round, and then when we start squeezing the model to output shorter and shorter execution traces, we're basically hovering around the same performance level of solving 93%, or slightly more than 93% of the test task. What's also interesting here is that the improved Searchformer model that only uses 450 million parameters is outperforming slightly, or is performing basically at the same level as a solution-only model that only has 757 different parameters themselves. So this is actually a much, much bigger solution-only model with far more parameters here. This speaks again to this idea of incorporating execution traces and how to compute a solution into the training data and make a model actually predict how to reason and how to solve a task overall. Now, this is really just evaluating how optimal or how well each model solves the test task set on Sokoban. Another thing that we also wanted to look at is another measure that really quantifies how much the system actually improves the trace length while also accounting for how often it actually fails to solve the task itself. Because what you could also observe is that when you start sort of pressuring the model to output shorter and shorter execution traces, is that it is actually not capable of solving the task optimally in the end, or even providing an optimal plan or feasible plan at the end. So this is where we sort of use an improved length ratio score that factors in the relative improvement over A* search. So we have here a number that counts how many tokens A* search would generate versus what the Searchformer model has generated here in green in that ratio, and then filter that with an indicator function to test if the task is actually, if the sequence actually contains an optimal plan that is also feasible, or only a feasible but potentially suboptimal plan. And then we just average that number across the entire test task set. And if we plot these numbers, or if we record these numbers for all of the tasks that were solved with a feasible plan, and all of the tasks that were solved with a feasible and also optimal plan, in other words, we reject all the suboptimal solutions from the right column here, we can actually see that with every improvement step, we're improving that score, and we're actually improving the model overall. So this is basically compiling the property of decreasing search trace length and increasing accuracy into one number, and we can see that we get a performance boost, or we get a ratio that is bigger than 1 and keeps increasing beyond 1, and therefore is actually an improvement over the initial model that started out with, let's say, a score of 9.0 or sorry 0.90 or 0.91 in this particular table. So in other words, the bootstrapping process seems to continually improve the model further and further. So in summary, just stepping back from these results, with appropriate training data, it is actually possible to train transformers to solve complex planning tasks, assuming you have correct synthetic training data sets that cast a controlled experiment. We also showed that it is very useful to include intermediate computation steps, and that will allows one to reduce the model's parameterization as well as the number of training tasks. So there are certain efficiency gains that can come from that, even if you have to actually include thousands of tokens into that. So like stepping back a little bit or looking back at the results that we had for the mazes, there we had thousands of tokens that the system had to predict and generate with in-context learning and autoregressive rollouts. And that while it still had to do that and make these predictions for these very long sequences, these models were still outperforming models that had to predict a much, much shorter string. So in other words, including this intermediate computation into the training data itself actually boosts performance quite significantly. And furthermore, we found that through these bootstrapping operations, we can fine-tune a language model to discover new and more efficient search strategies, meaning also this property of being able to basically explore the reasoning or the execution trace space is possible to use is possible using just a transformer encoder-decoder architecture that models some degree of non-determinism that is encoded in the training data itself. In other words, and this is different also to other work that has been presented before in reinforcement learning, we're using transformers really with the purpose of using them as the tool that allows us to generalize towards new execution traces and new ways of thinking or solving a particular task. And that allows us to actually bootstrap here and actually improve the model itself, just using the generalization properties that come out of of the language models that we're training on that synthetic data set. Lastly, one thing that I wanted to highlight here. Now, of course, like I said before, the goal is not really to improve or replace classical planning algorithms. Of course not, because we're pushing quite a lot of compute here in order to solve mazes with a deep learning model. But the goal with this project is really to start building that bridge between, or improve upon that connection between language models and sequential decision making and planning. And what we've shown here is that using language models, you can actually come up with new search methods that through this bootstrapping process to find more efficient or completely new ways of solving a sequential decision making and planning task. While at the same time, we hope that our results can improve our understanding of how we could endow language models with this ability to plan and to solve more complex reasoning tasks through these sort of very controlled experiments that we've been running. And with that, I'd like to again thank you for your attention. And if you have any further questions, please do ask away.
Thank you for the talk. We have a question in chat. Since the model has seen intermediate steps, if you train on 10 cross 10 and 30 cross 30, can the model generalize on 20 cross 20 mazes too? Can it not generalize if it is a solution only model?
That's a good question. Okay. The experiments are constructed such that we basically have, or the test, okay, so the tests that are included in the paper construct the test set using the same process as the training data that was generated. Now you could now say, okay, I want to prompt with different maze sizes, and there is a chance that, let's say, the 30 by 30 maze data set encodes or includes a smaller or effectively smaller maze. But right now, all we've known, or all that we know, what works well is if you stick with if the test test data set follows the same distribution as the training data set. That is not to say that they are duplicates between training and test data, but the process with which we generate them is statistically the same. So we don't know yet if that would work or not. With the solution-only model, probably it would work worse because we've seen generally across almost all of the sequences that we ran, all of the experiments that we ran, worse performance than if you were to include the entire execution trace into the data set itself. Okay.
Another question is in the chat is that can you provide some real life use cases where you think this model can considerably reduce compute time and help in producing optimal solutions?
Oh, I'm sorry. I think you broke up at the beginning. Can you repeat the first half again?
Can you provide some real life use cases where you think this model could considerably reduce compute time and help in producing optimal solutions?
Okay. Yes, of course. So what if you compare the search augmented versus the solution only models? The search augmented models are trained on larger, on longer sequences. That, of course, requires you to do more floating point operations during training, even though you have a smaller parameterization, but we get these better performance improvements out of that one. If you look at a solution-only model, the solution-only model is only provided with, here's the response for this perhaps very complex planning task, and then the system during training has to effectively infer the algorithm by itself. So in practice, that means if you wanted to generalize this insight towards other application scenarios, if you can provide the model with meaningful information in between of how to actually arrive at a particular solution, similar to what was shown also with Scratchpad, then you should be able to reduce the number of parameters over which you, and maybe even context lengths, over which you have to do inference, over which you would have to do inference at test time. And then you can get, if you train on data like that, you can get performance gains in practice through including these intermediate time steps or intermediate computation steps. What those are depends, of course, a little bit or a lot on the actual task that you're looking at.
One of the things that I had in my mind is that I read a paper recently that was on implicit chain of thought, where they basically do the chain of thought, but it is not produced in output token. So I think if something like that is here for the initial planning steps, but not the actual plan. So if
Yeah.
something like that is happened, we can maybe use the simple uh, simple transformer which produces less token, but actually has that planning capabilities.
Yes, that's right. That's right. Yeah.
If we don't have any other question, I guess we can conclude the session, right?
Okay. Thank you for having me.
Yeah, thank you so much for taking your time. It was a pleasure.
Hello.
Take care.
Excuse me. I just wanted to ask a small thing. Hi, Lucas. Would it be possible if I could just contact you later for research purposes? So if
Yes,
you could
of course.
provide some.
Of course, absolutely.
Thank you.
All right. Thank you, everyone. Take care.